Good day everyone. So today's topic is going to be pumping lemma for context-free grammar. So we have seen already pumping lemma in the topic regular expression. We have used pumping lemma to prove that a particular language is not regular. So here you should understand that pumping lemma cannot be used to prove that a language is regular for any grammar. So in the same way, in the similar fashion, here also we are going to use the pumping lemma for a context-free language. So we will be proving that the language is not context-free. Before going to what is context-free language and using with pumping lemma, we will see a small refresh about what is context-free language is. Your context-free language is a language that is generated by context-free grammar. So the set of all context-free language which are identical to the set of language that is accepted by the push-down automata. So the context-free grammar will be having four tuples V, T, S and P. So V will be a set of non-terminals or variable symbols, and sigma will be a set of terminals, and S will be the star symbol, and P will be the production rule. So in context-free grammar, the production rule will be of form A implies X, and we know that X can be either a set of terminals and non-terminal combinations, and A must be a non-terminal. So for this, if you are generating a language, then that language belongs to a context-free language. So you are going to use a pumping lemma. So let us see how pumping lemma is used to prove that a language does not belongs to context-free. So the pumping lemma for the context-free is, if a language L is context-free language, then it has a pumping length P such that the string S whose length is greater than or equal to the pumping length P. And it can also be divided into 5 pieces. So in regular expression, we have divided into 3 parts, whereas in context-free language, you will be dividing the strings into 5 parts. So here each string will be divided into U, V, X, Y and Z. So you can see here it will be divided into U, V and X and Y, Z. The following, so if you are dividing a string into 5 pieces, it must satisfy the following 3 conditions. So the first condition is, when you raise U and V to the power of I, X and Y to the power of I such that it belongs to the language for all I greater than 0. So you are going to have divided into 5 parts, and you will be taking it into, you will be raising the value of I, and if you raise the value of I, even then the string must belongs to the language. Then the second condition is the length of V and Y should be greater than 0, and the length of the parts V, X, Y should be less than the pumping length P. Now let us see the steps how we use pumping lemma to prove a language is not context free. We'll be using the contradiction. So what you will prove is, first we will consider that it belongs to context free. So the first step is, we assume the language is context free. Then if it is belongs to context free, then it must have a pumping length. It can be pumped with a pumping length P, so that all the strings that are longer than or equal to P must be pumped by the language, such that you can see the length of the string must be always greater than or equal to the pumping length. It should not be less than the pumping length. Then you will find a string such that, so we have to prove that it is not belongs to the context free. So you will choose a string such that the string length is greater than the pumping length. Then we divide the strings into 5 parts, U, V, X, Y and Z, and show that when you raise the V to the power of I and Y to the power of I for some values of I, it does not belongs to the language. Okay. If you try to prove that it belongs to the language, then it will become context free. So you will try to prove that it does not belongs to the language, then we can say the particular language is not context free. The next thing is, again you will consider the S and divide it into 5 parts and show we'll take different possible combinations of U, V, X, Y and Z and show that all the 3 pumping conditions cannot be satisfied. So if the string is cannot be satisfied, then the string generated by the language is not context free. Now let us see an example. We are going to show the language is not context free. So here the language which we are trying to use here is A of I, B of I, C of I. If you have same number of, if you have I number of A's, the same I number of B and the same I number of C should be available in the string. For example, the language generated by this grammar will be of form. So it can be equal to 0. So you can have an epsilon. So we don't consider epsilon because we are going to consider only string. When I is equal to 1, you will have A, B, C. When I is equal to 2, you will have 2 A's, 2 B's and 2 C's. If it is 3, you will have in this fashion. So it goes on, right? So we are going to prove the language is not context free using pumping lemma. So as I said before, we have to follow these steps. So let us follow the steps one by one. So the first step, we are going to use contradiction. So if you want to prove a language is not context free, we will take it as a contradiction that language is a context free. So the first step, we assume that L is context free. So if the language is context free, then L must have a pumping length. So it must have a pumping length. So let me assume it is going to be P, right? Now we have to take a string, okay, so which must be pumped with the length. So we take a string, we will take a string S, okay, such that it can be pumped with the length P. So how it will be such that S is equal to, so what are the terminals we can have in the language? A, B, C. So you will have A, B, C and each will be pumped with the pumping length P. Okay. Now what will be the next step? We have to divide the string. So you have to divide the string S into 5 parts. Okay, into 5 parts, into U, V, X, Y, Z. So how to do this? So we have to divide the string. So let us take an example. So we will take an example that my P is equal to 4. Then what is S? S is going to be AB, BP and CP. Here P is equal to 4. Then it will be A4, B4 and C4. Right? So we have to consider different combinations for V, X and Y. So let me take the case 1. Here V and Y each going to contain one type of symbol. Okay, you will be having one type of symbol. So what do you mean by one type of symbol? That means V should have only one terminal symbol and Y should have only one terminal symbol. It can be of multiple combinations, but the set of terminals should be one. So let me write an example. A, B, 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 B and C, 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 C. So why do I write this string? Because A4, B4, C4. So you will have 4 A's, 4 B's and 4 C's. So before dividing into 5 parts, you should understand what is the 3 things you have to prove here. So u to the uv, v is raised to the power of I x, and y raised to the power of I z should belongs to the language. The length of v and w, v and y should be greater than or equal to 0. Okay, and similarly the length of v, x and y should be less than the pumping length. So these are the three conditions. In such a way we will divide the strings. So we can take any combination, but the thing is we should have only one terminal symbol combination, and y should have one terminal combination. So let me take I will stick on with a itself. So let me take, I will take another color. Okay, I will take a blue color. Okay, now I will take these two as alone v. You can see only one terminal symbol is used and it is repeated. Similarly, I will take y. Y can be of anything. So let me take it as a single C. Okay, we'll take it as a single C. So I will take this one as y. So why do we mainly concentrate on v and y is because v and y are going to be raised to the power of I. Now what will be the rest of the symbol? So let me take on this first a alone as u. From the fourth a till the first c, let me take it as x, and the last two c's I will take it as z. Okay, so now what you are going to do here is, if u, v, x, y, z belongs to the language, then u, I to the power of I, x, y to the power of I, z must also belongs to the language for all I is greater than equal to 0. Okay, so this is the condition you have to go. So let me take I is equal to 2. Now I am going to raise it. So u single a, so this is u, and v is a, so it has to be v square. Okay, so you will be calculating u. Okay, just let me write the equation first. So you are going to find u v square x y square z. So what will be the string? What is u? U is a. Okay, what is v double a? So it has to be a. So this is v square, this is u, and the x is rest of the things. So a for b and c, which will be x. Then y is y square, so you have a single c, so it should be written twice. Then the remaining two c's is for z, so you will have two c's for z. Now how many a's, how many b's and how many c's are there? So a, when you calculate it, a is about 1 2 3 4 5 6, you have 6 a's, so a6. And how many b's we have? b4. And how many c's we have? 1 2 3 4 5, we have c5, where this is not in the form of the given language. You can see in the language all a and b and c should be of same numbers, but here we are having a is a 6, b is a 4 and c is of 5. All are different, so it does not belongs to the language. Hence the condition 1 fails for the pumping lamina. Okay, it fails, hence it is, hence therefore, okay, we'll take it as therefore the given language is not context free. Right, we have done for one case. Let us try for the other cases. So we'll try with some other case also, because we have to check with all other cases. So let me take the next case. So we'll have the second case again, some other combination, either v or y has more than one kind of symbol. So previously we used only stick on with one terminal symbol. Here we can have more than one symbol. So one kind of symbol. So let me write the string first. So we have said A is equal to A4, B4, C4. So S is equal to A4, B4, C4. So we'll write A, 4 B's and 4 C's. Now we are going to consider that V is going to have more than two symbols. So what we'll do, let us take, I will take another color for our example. Let me take this. So let me take two A's and two B's as my V. Okay, two A's and two B. And this one B alone, I will take it as X. Again, Y should be of some combination. So it can be either, we have said. So let me take it as a single string itself. So I will take this B alone as my Y, and the rest of the terms will be Z, and the first two A's will be U. So if U, V, X, Y, Z belongs to the language, then U, V to the power of I, X, Y to the power of I and Z must also belongs to the language for all I should be greater than or equal to 0. So we will consider, so you can take any value. I can be not only 2, you can take 3 or 4. It will be more big. So we will take a smallest value, or we can take 3. So let me take I is equal to 3. That means U, V cube, X, Y cube, Z. So this also should belongs to L. So we have to prove that it belongs to L. So we'll write U first. So U is going to be AA. This is U. What is B? AA, double B. So it has to be written thrice. So AABB. Again AABB. So this entirely is a B cube. And what is X? X is single B. And what is Y is single B? It has to be written BBB thrice because it's Y cube. And what is this Z is? It is Z going to be 4 C's. So 4 C's. Now let me count the A's. Before counting the A's, you just see here this part of the string, how it is there. You have some A's followed by B, then again A, then followed by B, then again A, followed by B's, then finally C's. This is not the form what is given by for our language. So what is the format we have to use is A should be followed by B, B should be followed by C. So AI, BI, CI. So this is the format of the given language, But I'll rub this. But you have a different combination here for the but you have, okay, we'll write but different format for U, V cube, X, Y cube, Z. Hence it does not belongs to the language. It does not belongs to the language. And condition 1 of the pumping lamina fails. Hence the given language is not context free. So this is how we prove a language is not context free using pumping lamina. Let us have another example. We will take another example to show how pumping lamina is used to prove a language is not context free. So see here, the language which is given is W, where W belongs to 0 or 1 terminal symbols. So what do you mean by W and W? So if the first word appeared, then it must appear the second time. So what will be the language it is generated as? So let us assume the language, if the first word is 0, then the second word must be also 0. If the first word is 1, the second word must be also 1. Suppose we have a combination. So if 0, 1 is a W, then you should have again a 0, 1. So we are not reversing or anything. We are just duplicating the string for the second time. So this is how we are doing. So you can have many combinations. So 1, 1, 1, 1, 1, 0, 1, 0, and you can have 1, 0, 1, 101 or triple one, triple one. It goes on like this. So this is the language that is generated by the given formula. So we are going to prove that it does not belongs to the context free. Okay, so solution, we have to prove that it does not, that language is not context free using pumping lemma. Right, so we are going to prove without pumping lemma. So we'll assume the steps. So we are going to take the contradiction. So we'll use the contradiction. So we'll consider the L is context free. So the step one is we will assume again L is context free. I'm sorry, it is context free. It is context free. Second step is, if it is context free, then language L has a pumping length. It will be having a pumping length P. Okay, pumping length, say it is P. Okay, so this is the second rule. If it is context free, then it should have a pumping length P. Now we can take a string of with the pumping length. So now we take the string as such that it is pumped with the pumping length P. So what is S is? S will be equal to WP WP. So what is W is? It is nothing but 0 and 1. So you will have 0P 1P 0P 1P. So the first one is for the first WP and the second one is for the second WP. So we will take it with the terminal symbol itself. Now we will divide the strings into 4 parts. So divide the strings S into, not 4 parts, into 5 parts. U, V, X, Y and Z. So let us consider the pumping length. P is equal to 5. So the string will be equal to 0, 5, 1, 5, 0, 5, 1, 5. Okay. So we'll take it as this. So the string will be 0, 0, 0, 0, 0 and 5 ones and again 5 zeros and 5 ones. So this is the string we are going to consider. So here we will consider with some boundaries. So what is the boundary is? So here you can see some boundaries are here. The boundaries are nothing but this one we consider as one boundary because zeros. After this you have another new terminal symbol. So this is first boundary. So I will write it as first boundary. This is second boundary and this is third boundary and this one will be your fourth boundary. Now your V and Y should lie in which boundary? It should lie in the same boundary or it should lie in different boundaries or it can be in the midpoint because we have two words here, W and W. So you should understand where V and W. If you take V in first W and Y in Y in the second W, then we can prove it is context free. So we are here to prove that it is not a context free. So what you will do is we will try to choose across the boundaries. You will be trying to choose the across the boundaries. So let me take case 1. V, X, Y does not straddle. Okay, so straddle or cross or either side, does not lies on either side a boundary. So it must lie within a boundary. So I can choose any boundary, right? So let me choose the boundary for this. So let me choose it within the ones. So first let me write the numbers. So I will take 5 zeros, 5 ones, again 5 zeros and 5 ones. So let me choose my V, X and Y lies within a single boundary. right? So it should lie within the boundary, it should not cross the boundary. So how do we choose it? So let me take another color and I will prove. Let me consider that this three parts lies in a single boundary. So here v is going to be 1, x is going to be 1 and y is going to be 1. So the remaining term will be u, and from this one to the last one will be z, right? So you are choosing y z. So the second condition, what is the second condition of the pumping lamina? The yv should be greater than or equal to 0. Here it is greater than because v is 1 and y is 1. So the length of vy is greater than 1. It is true. So it is true. So I will write pumping lamina condition 2 here. And the pumping lamina condition 3 is Vxy. The length of V and xy should be less than the pumping length. So what is the pumping length? Pumping length is 5. Here the total length is 3. Hence it is also true. Now we have to check with only the condition 1. What is condition 1 is if u, v, x, y, z belongs to the language, then u, v to the power of I, x, y to the power of I, z must also belongs to language for all I is greater than or equal to 0. So what we'll be doing, we'll raise the value of I and prove that whether it belongs to the language or not. So we'll show whether it belongs to language or not. So what I'm going to do here is I will take my I is equal to, that is u vi square x yi square z. So we'll take I is equal to 2. That means u v square x y square z. Now what is u? U is 50 plus 1. So we will write it over here. 0, 0, 0, 0, 0, 1. And v, x and y are 1. So this is u. V is 1. So it is v square. So you will take v square. And x is 1. So this is x. And y is again y square. And what will be z? 1 followed by 5 zeros and 5 ones. So we will write it the same way here also. 1, 5 zeros and 5 ones. So this is Z. Now let us count how many zeros and how many ones are there. So first you can see it is having 1, 2, 3, 4, 5. So it is having 0, 5. How many ones are there? 3, 6, 1, 6. Is it 1, 6? No, 1, 7. You have one more 1 in here. Okay, so you'll have 1, 7 and 0, 5 and 1, 5. So it's very clear that it does not belongs to the language, since 0p, 1p, 0p, 1p. So the first half should be repeated second half. Here you can see 0 and 1 itself is not in the same format, hence our condition fails here. Now let us consider the second case. We will take another case over here. Let me have the second case. In previous case, v, x, y were straddled to a single boundary. Now let us cross the boundaries. So v, x, y straddles the first boundary. So let me tell, we'll have 0, 0, 0, 0, 1, 1, 1, 1, 1, again 0, 0, 0, 0, sorry, 0, 1, 1, 1, 1, 1. So v, x, y should cross the first boundary. So this is the first boundary. Okay, so this is the first boundary. So it is going to cross the first boundary. So let us take, I will take the first two is u. Okay, and v will be, I will take v as 00. So I will take v as 00. Let me take x is 1. Okay, let me do like this. So you know, cross, you will take the first 3 zeros as u, then we'll take two zeros as v, we'll take single x, then y you can take again two ones as y, and the remaining terms are z. So what you have to do here, u v to the power of I, x, y to the power of I, z should belongs to language for all I is greater than 0. So let us take I is equal to 2. So u v square x y square z. So s will be, what is u double zero? So double zero, this is u, sorry, triple zero. And what is v is double zero? So you'll have double zero and double zero. Okay, let me write it in the next slide. So we have to take, let us take I is equal to 2. That means u v square x y square z. So what is u? U is triple zero. So we'll take u is triple zero. So it is going to be triple zero. This is u. What is v is? V we have taken it as double zero. So you'll write double zero as v square, and 1 is x, and double 1 is for y square. So now what is z is? We'll check what is z is. Double 1, 5 zeros and 5 ones. So we'll write that double 1, 5 zeros and 5 ones. So this is your z. Now let us count it. So how many zeros and how many p's we have? 1, 2, 3, 4, 4. So you have 0, 7 and you have 1, 7, but followed by 0, 5 and 1, 5, which does not belongs to the language, since the first word is not equivalent to the second word. So our case 2 also failed. Right, let us see the third case. Now we will take another example. Our case 3 is going to be that v, x and y is going to straddle in the third component, okay, the third boundary. So let me write it. So I will write 5 zeros, 5 ones, again 5 zeros and 5 ones. Right, so third means, okay, here it is third and this is fourth, so it is going to straddle over here. So what I'm going to do here is, I will take these two as v, I will take 1 as x, and again 2 ones I will take it as y. The last 2 ones will be z. So from this part to this part it will be u. So from this we are very clear that the condition 2 and condition 3 is satisfied. So what is condition 2 here is, the bx y, it should be less than or equal to the pumping length, it is true, and b and y is greater than 0. So you have to check for the condition 1 only. So the condition 1 is, if u v x y z belongs to the language, then u v to the power of I x y to the power of I z must also belongs to the language for all I is greater than 0. So what we will do here is, we'll increase, again we'll take I, because the string is too large, so we'll take I is equal to 2. So u v square x y square z belongs to the language. We have to prove this. So we'll write the u first. So what is u here? 5 zeros, 5 ones and 000. Okay, we'll write that. 5 zeros, 5 ones and 000. Okay, so this is your u. And what is v is, we took it as 00. So you will have 0000 as v square. X is 1 and y is 11, so you have to square it, so y square, and z is 11. Now let us count the number of zeros and number of ones. You can see here 0, 5, 15 and it is 0717. Okay, it is counted 0123. Okay, right, and it does not in the form of the given language. Okay, so the first word is not equivalent to the second word, hence it is not belongs to the none. So let us see the final case. So my final case 3 is Vxy straddles at the middle point. Okay, it straddles in the midpoint. We are going to take with the midpoint, so it is going to be in the middle. So 0 0 0 0 0 5 ones, 0 0 0 0 0, again 5 ones. So the midpoint is this. It is going to be lying between this. So let me take again here. We will take this V as V. We will take single. We'll take it as midpoint. No, so we'll take. If you take it like anything, you can take. So let me consider this 2 is V, this is X, and this 2 is Y. So rest of the terms are going to be my U, and my rest of the terms are going to be my Z. So if U, V, X, Y, Z belongs to the language, then U, V to the power of I, X, Y to the power of I, Z must also belongs to the language for all I is greater than 0. So we take I is equal to 2. So U V square X V square must belong to the language. So this is what we have to prove now. So we'll write U first. So what is U? 5 zeros, 1 1. So this is your U. What is V? 1 1. So it is V square. X is 1. What is Y? 0 0 0. It is Y square. And Z is 0 0 0 and 5 ones. It's Z. Now let us count the zeros and ones. You can see it's 0 5 1 7 0 7 1 5. You can see the first word is not equivalent to the second word, as well as if it is 0p, then it should be 1p. Here that is also not there, so it does not belongs to the language. Hence we have proved for all sort of cases, hence the given language. So we'll so all the possibilities the cases for the string does not satisfy the string, does not belongs to the language. It does not belongs to the language L. Hence it is a contradictory to the first step. We assumed that L is a context free. So here it is a contradiction. So L is not context free using pumping lemma. So which is proved using pumping lemma. So I have given enough example for the pumping lamina. Hope you understood. Thank you. We will see a new topic in the next session.